Okay. So Pepa has asked me to introduce our speaker to you. So we have here today Dr. Mahmoud Oshagh. He comes from Iran, where he did his studies on physics in general, and then in 2010 he left to go to Porto University to do his PhD, which he did with under the supervision of Nuno Santos and Nader Hagigipur on, in general, was stellar activity, the impact of stellar activity in exoplanet research. And then after he finished in 2014, he was awarded a grant at Göttingen University to continue these studies, of which he's going to talk to us about. So without any further delay, I give you the floor. Oshagh.
Introduction, and thanks for giving me the opportunity to talk about my research. And as he said, my talk is about impact of stellar activity on our understanding about exoplanet, on different aspects of it, from detection and also to characterization of them. But before I go to that, I will briefly introduce the two main techniques to detect exoplanet. The first one is named radial velocity, which is based on measuring the Doppler shift in the spectral line and attribute that to the movement of the star due to the presence of the planet around it. So if you measure the Doppler shift or the radial velocity time series, there are two main parameters of the planet that you can get. The first one is from the periodicity of that signal, you can estimate the orbit of the planet, the period of the planet. And the second one, from the amplitude of that radial velocity variation, you can estimate the mass of the planet. So if the planet is more massive, the signal will have much higher amplitude. But from the radial velocity, we don't get any estimation on the size of the planet, on the radius of the planet. Since the beginning of the exoplanet era, at the beginning, since the instrumentation precision was not that high, people were detecting those massive planets because they are producing higher signals. So there were Jupiter-sized planets on very short orbit, known as a hot Jupiter. But as the instrumentation precision improved, nowadays we have the instrumentation to detect Earth-sized planet on the one-year orbit around the solar type star with instruments such as Espresso. But I will tell you later that why now that we have this instrument, we still cannot detect them, because there are some things blocking us from detecting Earth twin. The second technique to detect planet is named transit method, which based on observing a passage of a planet in front of its host star, and it causes a reduction in the brightness of the star. And from the depth of this transit light gap, you get very important information, which is the radius of the planet, because the depth is proportional to the area that you cover. So you can easily get the radius ratio of the planet. But detecting planet from transit technique has two issues. The first one is that if the planet has a different inclination towards the observer, we will not observe it. So if it passes a bit higher, due to the inclination, we don't observe the transit. And also, if you observe the star, but you don't observe it during the transit of the planet, but you observe it during the rest of the orbit, you miss the transit, so you miss the detection. So to overcome these two issues, the large surveys, such as Kepler, came to the play. So Kepler was a space telescope which was observing more than 150,000 stars for over 4 years, every half an hour. So that overcome all the issues that I mentioned, and as you can see, it improved the detection of the transiting planet by order of the magnitude. And also, so you can see the yellow one are the Kepler detection. And also due to good precision of the Kepler, we were detecting much, much smaller planet. So before Kepler, we were mostly detecting Jupiter-sized transiting planet, but with Kepler, we were able to detect even Earth-sized planet. But there is another issue with the transit technique, which is when you detect the transit signal, it can be due to other physical phenomena, which mimic your transit light curve. So there are astrophysical false positives, such as the low mass binaries or background eclipsing binary or grazing binary. So in order to understand if the transit that you are seeing is due to a planet, either you should do the radial velocity confirmation of the system to get the mass and see if the mass of the planet is in the range of the planet, or you should do sophisticated statistical validation of the system. But when you confirm the existence of the planet in the transiting planet, so you have the mass of the planet and you have the radius. So you can go one step further and estimate the bulk density of the planet, which is the important criteria of the planet, because then you can do the comparison between them and categorizing them, and also do the comparison with the solar system planet to see what is the composition of them and what is the interior structure of them. But from the beginning I said these are all affected by activity. So I move now to the section talking about how activity is affecting all of this. Stellar active regions, such as those that we know on the sun, they appear also on other stars that they have convective zone. The spots and also the granulation pattern that we know on the sun, they appear on the others, and how they can produce the radial velocity noise. The active region, they can produce in two mechanisms the radial velocity noise. The first one is due to their contrast. So when you have a rotating star, so you have a blue shifted part and the red shifted part. So this part is coming toward us and this part of the star is going away. And if you have a dark spot on the surface, you have less photon from that region, and that block a part of your spectral line, the blue shifted part. And when the star moves and the spot goes to the red shifted part, you have a deformation in your line in the red shifted part. And that introduced a radial velocity signal in order of meter per second signal. The other thing that the active region can produce is due to the granulation pattern. If you look at the sun, there are those granulation movement because of the convective motion, that the hot material come to the surface of the sun and they cool down and go down. So you have a constant movement of the hot material. And since the hot material are brighter and also they cover larger surface in the granulation pattern, you have a net blue shift on the sun. So if there is no active region, you have a net blue shift of 300 meter per second on sun. But but that is constant. But when you have active region, because of the convection, it stops the convection motion in that region. So you break that net blue shift, so you introduce another signal, which can be also in meter per second level. And this is what we know from sun. So this is the RV noise that we get just assuming the spot contrast on sun, which can produce up to 2 meters per second noise. And that is due to the second effect that I said before, the convective blue shift. And that can be up to 10 meters per second. So for sun, the main source of the noise is not because of the contrast of the spot, it's because of the blockage of the convective motion. And you see that in the total RV noise of sun, the dominated one is the convective blue shift. And here you see the signal from the Earth on 1 year orbit. So you saw that what is a problem now to detect Earth twin. So we want to detect this signal, which is dominated by the noise from the star. So it's much, much harder than just having the instrument able to detect that. And here is an example that how an activity signal can look like a planet signal. So these are, the amplitude are similar, the periodicity is similar, but one of them is just because of the activity of the star, and the other one is because of the planet. So it's really tricky business to find planet, because you can find something, and then later there is an example that it was just activity, and I will give you two funny examples of that. This is a Coro 7 system. It's one star which is believed to have 2 planets. So this is the first planet and second one. And you can see the estimation for the mass of the planet. So from the study to other study, the mass estimation can be 3 sigma far from each other for both cases. And also in some cases, they don't find that planet, but the other find a very massive planet. So it's interesting how they miss it. And it's interesting to know that several of those studies, they use the same data set. So it's only the matter of how they treat their data, how they correct the activity, they were getting different mass or different number of planets. And the other case is Alpha Cent B that was announced in 2012 that it has an Earth mass planet, but then later was shown that it was the artifact of how they correct the data and also from the instrument. So if you don't want to get the red flag on your ESO press release, you should be very careful because then later you will have this. But there are classical ways to understand if the radial velocity signal that you get is from activity or is from the planet motion. The classical way is to look if there is a correlation between your radial velocity signal and any other activity indicator, such as the line, spectral line deformation indicator, like the bisector, or looking at the S index or log R prime HK index. And if you see a correlation, it shows that, okay, your radial velocity is coming from activity. And you should be careful. But if you don't see a correlation, you can be confident that your radial velocity is purely because of the gravitational movement. But the problem of this is that in some stars, you see correlation between your radial velocity and some of the indicator, but the other indicator, they don't show anything. So there is an issue that which indicator is the best one, and for which type of a star, which indicator works better. So this is an ongoing field of research. But in 2016, Raphael Haywood shared a nice study to use sun, because for sun we can resolve this disk, so we can study which activity indicator for sun is good. So she did a study using the reflected light of the sun from the Vesta asteroid, observing it with the HARPS instrument, and also using simultaneous SDO image of the sun. So she obtained the radial velocity of sun as a star, and also the whatever we can get from the resolved image of the sun. And the interesting thing, she found that those classical activity indicators, they are not good activity indicator for sun. They show some correlation, but they are not that significant. But the best one, the best activity indicator is the magnetic field of the sun or the filling factor of the active region. So these are the two best activity indicators for sun. But the problem is that these are the two most hardest to find on other stars, because on other stars we cannot resolve the disk, so we cannot find what is a filling factor of active region. And also finding the magnetic field is not that easy. You should have a fast rotating star, and for sun-like a star, it's really hard to get the magnetic field. So to see also if having high precision photometry could be a good activity indicator, we use the opportunity that the K2 mission. The K2 mission is the successor of the Kepler. After the 4 years of Kepler mission, that the reaction wheel failed. Now the Kepler telescope is observing in different field of views, and it's named K2. And for first time, it was able to observe southern hemisphere. So we used that opportunity to perform simultaneous K2 and HARPS observation to have the most precise photometry and most precise radial velocity to see if there is any correlation between photometry and radial velocity. And here are some examples of, we did it for a sample of star, and here is what we found. So here is the x-axis is the photometric variation. So when it's high, the photometric observation was showing high variation. And here is a predicted divided by measured radial velocity. So when it's close to unity, it means that we are predicting quite well. So what we found that for a very active star which shows huge photometric variation, it is easy to predict the radial velocity jitter. So it means that the star is dominated by spots So it produced huge photometric variation, and that helped to predict the RV jitter. But for quiet stars that they are photometrically quiet, it's not that easy to predict the radial velocity. So the photometrically was quiet, but the radial velocity was very, very noisy. So the only way to model them quite well is as you see the blue points, is to consider that convective blue shift that I said. Because if you have active regions which are not very contrast, they don't produce photometric variation. So the photometric variation is small, but they still produce huge radial velocity signals. So this could be a confirmation of presence of two populations of the star, the one that are spot dominated and the one that they are facula dominated, or the plage dominated, which are not very contrast, but they still have that convective blue shift effect. The other thing that we used our observation was to use the F8 index. This is a new index that it was introduced by Bastien in 2013. It's a very simple index. It just measures the variation in your photometry during 8-hour window. And they believe that it can have a good correlation with the surface gravity of the star, because that 8 hours is a time scale of the granulation. So if you measure your photometric variation during that 8 hours, they found that it has a good correlation with the astroseismic surface gravity that you obtain independently. And since then, this F8 has become a useful index to get the surface gravity of the star, which we don't have the astroseismology observation of them. And later it was shown that this F8 is a good indicator for the RV jitter. So if you have the F8 measurement during just 8 hours observation photometrically, you can predict quite well the RV jitter. And also we show that that F8 correlates well with the photometric variability. So just 8 hours observation photometrically can give us useful information about what is going on the star. So this could be a good new activity indicator. Now I go to the second technique and the transit, and see how stellar activity affects the transit technique. So when you have the planet transiting, if the star is not a uniform disk, and if it has some feature, but you are not overlapping any of those features. So presence of those dark spots reduce the brightness of the star. So you are passing a star which is darker than its usual, so the transit depth becomes much deeper. So it will cause an overestimation of the planet radius. In the case of this Coro 7 that I told you before, during the time that the star was very, very active, you cannot see the transit here, they are very small. But these are the photometric variation because of the stellar rotation. During the period that the star was very active, the planet radius was overestimated by 20% compared to the period that the star was a bit quiet. And that is a bit scary because you can misclassify the planet that you find. Because if you find the planet during this period, it's a completely different planet that you find it during the other period. But the other scenario that can happen is that during the planet transit, you overlap with those active regions. And since Kepler was providing very high precision photometry, we were able to detect those anomalies in the transit light gap. So when the planet passes over them, you see them. And you see also their movement from transit to the other transit, which shows how they are changing on the surface of the star. But we did some simulation to see how much it can affect our estimation, because people were not taking into account them, and still they were fitting a model which ignored that effect. And we show that it can cause underestimation of the planet radius, because if you fit a model which ignored that, it will compensate it by modeling a smaller planet than its usual. So it's a bit opposite to the other effect, that it was overestimation of the planet radius. But from transiting planet, you can get another interesting thing, which is the transit timing. So if you measure the transiting of the planet times. And if it's periodic, strictly periodic, it shows that the planet is alone because there is nothing perturbing its orbit. But if you measure the transit time, and each time it happened on different period, at different times. So you measure a transit timing variation. That is an indicator that there is another body in the system which perturbs their orbit. And this is a technique to detect exoplanet, which is called TTV. And you don't see the other planet because it's maybe further away and it doesn't transit. So you just see its effect on the transiting planet. We did, again, simulation and show that the spot anomalies in the transit can cause a transit timing variation because if your model tries to compensate it, it causes a shift. And it can be up to 200-second fake TTVs because of the activity. You might say, okay, 200 seconds is not that big in the transit timing changing, but that is exactly the signal you want to detect if you want to detect the Earth-sized planet causing a TTV on the Jupiter transit. So it was a kind of alert for people detecting TTV planets that if the star is active, you should be careful because you can find some fake planet just because of activity. And later it was shown even that stellar activity, this is a TTV signal, which if people were not aware that the star is active, they could say, okay, it shows a TTV signal and it's periodic, but it's exactly just because of the activity of the star. So it even can produce a periodic TTV signal. Okay, now I will move to the other property of the transiting planet which we can get. When you have a transiting planet, and as I said before, a rotating star, you have a blue shifted part and a red shifted part. So if you observe a transiting planet spectroscopically, you can obtain a signal which is known as a Rossiter-McLaughlin effect. And this is because the planet, when it transits, first it blocks the blue shifted part and then it goes to the red shifted part. And it's around the transit time that it happens. This is very important phenomenon because in solar system we know that our planets are in the disk of the sun rotation. So we are kind of aligned with the sun rotation. But if the planets are not aligned and they have different spin-orbit angle, the Rossiter-McLaughlin shape will be different because if you assume a very misaligned planet, it just blocks a redshifted part of the star during its transit. So if you observe the Rossiter-McLaughlin, you will observe this shape instead of a very symmetric shape. So it's a very powerful technique to measure the spin orbit of the system. And it has been used for hundreds of exoplanets. And you can see that, I mean, these are real observations of aligned planet. And here is an example of very misaligned planet. And here you see a trend that planets which orbit a cooler star usually are aligned, like our solar system. But if they are orbiting a very hot stars, the misalignment can be high. Even they can be retrograded. So they can orbit in the different direction of the star. And this is still an open question how to explain this trend for a hot star and cool star. But as I said before, during the transit, you can have those occultation with active region. And that can happen also during the Rossiter-McLaughlin effect. So in the transit, you see a bump, but in the Rossiter-McLaughlin, you have to see also a bump. But the problem is that the Rossiter-McLaughlin observation does not have that much good sampling. So you might miss them because of the bad sampling also, and also because of the error bar in your radial velocity measurement. So we did simulation to see if those spot crossing happen during a Rossiter-McLaughlin, how much it can affect our spin orbit angle. And we found that it can cause a aligned planet like our solar system just because of activity to look like 40-degree misaligned. So this was just pure simulation, but it was convincing enough that the OPC gave us time, 6 nights on HARPS, to do consecutive Rosetta-McLaughlin of transiting planet, which they transit very active star, to see if we can measure variation of this spin-orbit angle from night to night. Because if you detect it, it shows that, yeah, so the activity is causing this spin-orbit variation. And we did it for 6 systems, and you can see here example of Rosetta-McLaughlin from one night, the next one, and the next one. And here is the spin-orbit angle. You cannot see it well, but here you can see it better. So for some cases, the spin-orbit angle, which is the value here, can be from one night to other night can be up to 60 degree different. So one night it's plus 30 degree, and the second night is minus 30 degree. And that was a good result we find, because usually when you do simulation, you overestimate things. But this time, we underestimated, and the observation is showing much, much higher than what we expected. So yeah, the stellar activity can cause a planet changing its, at least estimated spin-orbit angle can be different from transit to the other transit. But we were lucky because we observed some of our Rosetta-McLaughlin that we observed it simultaneously photometrically. And that is a powerful thing because, as I said, the sampling in our Rosetta-McLaughlin is not that good. So we cannot see any occultation with the spot, but we can see it clearly in the photometric observation, which has a higher sampling. So if you see it, for sure the planet is passing over 3 spots because we model it with that. And if we try to model those spot crossing events in the photometric observation and looking at its corresponding model, you see that it's modeling the data much better than a model that does not consider any spot crossing. So it shows that how much is powerful to observe simultaneous transit with your Rosetta-McLaughlin, because in the photometry you can get much, much more information about spot occultation, and then that can be used to model the Rosetta-McLaughlin. Now I will move to the planetary atmosphere. As I said before, if you obtain the mass and radius of planet, you can do the bulk density of the planet. But that is not enough, because if you look at our solar system, there are planets that in this mass radius diagram, they are close to each other. So you would guess, okay, they are same. But when you observe their atmosphere, that you see that they are completely different. So studying the atmosphere of the planet, it could be a way to distinguish different type of the planets. And one of the most powerful techniques to study exoplanet atmosphere is transmission spectroscopy. This is based on observing the transiting planet in different wavelengths. As I said before, the depth of the transit gives us information about the radius of the planet. And if you observe the transit in different wavelengths, you obtain the planet radius as a function of wavelength. And that can give us the transmission spectra of the planet. Here is a transmission spectra of the Saturn, which was observed during one of its transit over Sun. And using the transmission spectra, you can estimate presence of some molecules and atoms in the atmosphere, and also thermal structure of the atmosphere. For exoplanet, it has been used for several exoplanets to study their atmosphere. And as you can see here, different lines are different exoplanets. And there were detection of the sodium, potassium, water in the atmosphere of several planets, and also titanium oxide. And this is from last week, that there was a first detection of the helium in the atmosphere of a planet. So this technique is really powerful. And one thing that a lot of planets show is an increasement in the planet radius towards shorter wavelength, which is known as a Rayleigh scattering in the planetary atmosphere. So those planets which they show this slope, they are the blue sky planets, similar to Earth. But the problem is that the stars are not, as I said before, are not uniform. They have those active regions, which now in the transmission spectroscopy, not because of their contrast, but because they have different spectra, if you are overlapping with them or not during the multiband photometry, it will significantly affect your transmission spectra that you observe. And this is a very important fact because it has been shown that those active regions can easily mimic the spectral feature that you want to observe. So this is an observation from HST of one planet, the points, and this line is just because of the activity. So it produced exactly what you observe. So it's not saying that this planet does not have any atmosphere, but it's just saying that activity of the star can mimic the transmission spectra that you want to observe. So you should be really careful to see if you can disentangle these two. The other technique to obtain the transmission spectra is to do chromatic Rosetta-McLaughlin. As I said before, the Rosetta-McLaughlin is transit observation in the spectroscopically, but if you do it in different wavelength, the amplitude of the Rosetta-McLaughlin depends on the planet radius. So you can obtain the transmission spectra using the chromatic Rosetta-McLaughlin. And this was done just for one case, so it's really new method. And it showed a good agreement with what was obtained with HST observation. But similar to the photometric multiband observation, the chromatic RM also has an issue with stellar activity. Because if you have a stellar activity, it can induce a slope out of your transit, and that can, again, mimic those features that we saw here. So these were from multiband photometry that mimic this line. And here we see that this chromatic RM also can be affected by the stellar activity and mimicking different trends. So if you have a stellar activity and you are looking for different feature in your transmission spectra, stellar activity can mimic a lot of those broadband features. But the good thing is that, or those small features such as the absorption of some molecular bands, we are not sure that the stellar activity can mimic those. So this is still an open question, that those broadband features can be mimicked, but those absorption line, we are not sure that the stellar activity can mimic them. Because if it can, then it will be an interesting topic of research. So now I will move to the last part of my talk, which is a bit different. Now I'm not talking about how stellar activity can affect the planet. Now I'm talking how to use the planet to understand better the star. Because as I said, planet, those that they transit, you can use them to probe the stellar disk because they can provide information what is going on the surface of the star. Here you see the Kepler observation of one star, and this is the photometric variation because of the spot on the surface of the star as a function of time. So at some point the star was very active, so the photometric variation due to the rotation was higher, but then the star was a bit quiet. But again, so you see kind of cycle in the photometric variation of that star. But that star has a planet. So if you zoom, you would see those transiting planet signal. And if you zoom, you see the transiting signal shows those bumps. So it shows that the planet transit those active regions. So we want to see, by measuring those anomalies inside, which provide information how much spots were covered, were overpassed by the planet, and information from this photometric variation of the star. So this is a bit confusing plot. So this is a photometric variation outside of the transit, and this is what is inside the transit. So if I go back, the x-axis shows how much photometric variation is from the stellar rotation, and the y-axis shows how much inside transit was noisy. But, so what we found is that there is a kind of strange behavior, because we were expecting when the star is very photometrically active, so when we are looking at this period of the star, the transit should be also messy because there are more spots, so you should have a lot of those features. But we found the empty space kind of here. So when the star is very active, the inside transit is not that messy, which was interesting. But we thought maybe, we are thinking wrongly. So we tried to simulate this. So we have a code that can simulate exactly what we observed. So we have a star that shows the photometric variation, but with the cycle, so it goes down and up. And also a transiting planet which pass those active regions. And what we obtained that the simulation shows what we were expecting. So when the star is photometrically very active, your inside transit also is very active. But it's opposite to what was observation. So this empty place on the right up corner in the observation, it's a bit strange. It should not be there from simulation. And we have a possible explanation for that. So if the star is photometrically active, there are spots, but they are huge ones, but not that many. So when the star is rotating, it produces huge photometric variation, but when the planet transits, since there are not that many, the transit is clear because there are not that many spots to overpass. But when the star is full of spots, if you rotate this star, it does not produce that much photometric variation because when one of them goes behind, the other one comes. So that does not produce huge photometric variation. But when the planet passes, there's a huge noise inside the transit. So this is a possible explanation that when the star, for example, here, become quiet, it's not really quiet. It's just full of spots. So we don't see the photometric variation. But here, it's not more active than here. So that is something new, but we need to explore this more to see if there is nothing else biasing our observation. The other thing that we used was using the inside transit anomalies and to see if that provides information about magnetic cycle of the star. So one of the stars that we observed, the inside transit variation was showing kind of periodicity. So if you do the periodogram of the signal, you see a clear peak around 390 days. And we were happy that, okay, this is a good method to detect the magnetic cycle of the star just using transiting planet. So not using any information from the photometric variation of the star. But the problem of this technique is that, especially using the Kepler, that you are affected by the noise of the CCD. Because Kepler was rotating every 90 days to just block the sun. So every 360 days, the star will fall on the same CCD. So if the CCD has a different noise, and since we are using the noise inside the transit, we would detect this kind of 360. So if the star has a magnetic cycle around a year, we cannot detect it with Kepler. But if it has much longer, but there is an issue that Kepler just observed 4 years. So yeah, this is interesting because it can be a new method to detect the magnetic cycle of the star, but we should be careful that not detect just the Kepler rotation. And that's it.
Thank you for the talk. I guess that the variation due to activity is much more wavelength dependent than the variations due to planet presence. So, and of course, they can also be different in the epoch dependence. So this wavelength dependence and the epoch dependence can be used to discriminate better, I guess, between activity and planets, and can even eliminate the confusion between them. Is it?
Most of the observations are very expensive in time of doing. So people sometimes they just do one transit with HST, and they don't have multiple epoch observation. But for sure, having that, it's the best way to distinguish, because the star activity is wavelength dependent and also is time dependent. So it changed by time, but the presence of the planet is not. So.
They are expensive, but I guess that also the need to announce the discovery of a new planet immediately and not have patience is not only so money is not only the only argument in that respect.
Well, actually, this chromatic effect that you see in wavelengths from activity, the longer your wavelength coverage, the better, because you can discriminate much better if you have a longer wavelength. And we are using it in Carmenes, for instance. We cover the optical and the near infrared, and we are trying to try to correlate this wavelength chromatic effect from activity and to try to correct from it our radio velocity data to try to get the planets, the signal. The planet from the signal from the planet behind the activity signal that we are using. Any more questions? Yeah.
Okay, it's a very nice talk. I have one thing which wasn't very clear for me. It's the blue sky mimic. The first thing I don't understand what the physics behind that, and the second one, how it's comparable in the two figures that you show when we see the effects of the atmosphere and we shoot the, yes.
I mean, you observe the transmission spectra and you have the increasement of the planet toward the shorter wavelength. That can be an indication of the radial scattering.
Yes, I understand.
Yeah. Yes. But if you have a spot also in the blue wave, in the shorter wavelength, that is more contrast. So it can produce the effect on the planet radius. It can affect it much more significantly than the red wavelength in the infrared. So it can produce exactly the same slope that you observe just because of activity. So it can be that these observations are not because of the radial scattering in the planet atmosphere, it's just because of the spots on the star.
And how do they compare the number, the absorption due to the Rayleigh atmosphere and the absorption due to the spots? Is it the same scale?
The data is, yeah, it's exactly the same. Yeah.
Yes, I'm seeing the number difference, so I wasn't sure about the scale.
Data points are the data observation, and the line is the spot model.
That's very interesting.
Yeah. But, regarding this issue, then for an active star, where we know that activity changes from epoch to epoch, this slope should change also.
Yeah, that is the point. But as I said, some of these are just one transit observation, which is HST. So yeah, if we have multiple, and if it is always in the same, we cannot say it's always activity, because to produce it with activity, we should be very unlucky that always it's happening at the same configuration of spots. Or yeah, so that is for sure. Yeah.
Concerning the hypothesis about the rapid variation in the period that was, I think, this one. Okay, this one. Okay. It's possible to find a star with so many spots that you draw that, or it is an hypothesis? In other words, what is the star with the largest number of the spots, for example?
Some studies using the Zeeman observation that they were showing that this is somehow possible, and they observe it for some stuff. But I don't know how common it can be, and also depending on the spectral type, which spectral type show this, we don't know. It's because this trend that we found, it's a combination of several stars. So each color is different star with different spectral type. So if it is showing it for different spectral type, this is a bit, tricky explanation. So I cannot say that this is for sure true, because to extrapolate it for all spectral type, it's a bit difficult.
Yeah, actually, I had one question regarding exactly this plot, because it's been shown that very active stars, some kind of very active binary stars, which co-rotate with the orbital period, can show polar spots. These are very, very big, very large spots at the poles of the star, and also bands of spots. So I was thinking that maybe another test could be not just going from the picture on the left to the picture on the right. No, on the other one, yes, but going from few small or smaller or larger spots, but very few, to polar caps and bands of spots, and see if this also provides different results from a homogeneous coverage of smaller spots.
If you go to the polar, also they can produce less photometric variation. So yeah, that could, yeah, I can test that if it shows different trend. And yeah.
What you need is distribution along your
Yes. Not yeah.
Okay. Any more questions? I have a final one. Okay. So if you go to the spin orbit angle alignment issue. Yeah. Okay. Well, when you show the alignment with the temperature of the star, so that there is some trend suggesting that hotter stars show different alignments compared with cooler stars. But you were saying that activity may make planets look misaligned with respect. I mean, with respect of planets orbiting stars that don't show activity. But in fact, here you see misaligned systems for hotter stars that shouldn't present activity, or so there is something there that is not quite fitting.
Yes, but the thing that we found from our observation is not just the activity cannot just make an aligned planet look misaligned. It can also make a misaligned planet look aligned. So it can be also that it brings all. So maybe there are points here, but because of activity they are down. So maybe there is not at all any trend. So they are just randomly distributed. But because of activity they are brought down.
So in principle they shouldn't be affecting the blue parts of this plot, but the cold side of the stars there. Okay.
Also, I mean, they are all hot Jupiters, and yeah, so it's. I mean, this picture can be different if you observe longer planet. I mean, yeah.
Any more questions? If not, we thank our speaker again. Thanks.